Okay, so let's wait for 2-3 minutes. Let's see how many joins. Then we will start. Hi, am I audible? Hello, am I audible? Can you please type something?
Audible and screen visible.
Okay, so we will start in 1 minute. Let's see if anyone else joins.
Okay.
Okay, so let's start. So hello everyone, my name is Rajat Mukherjee and I'll be taking this live session for NPTEL course on reinforcement learning. I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. This is sort of a tutorial. I will be doing a recap for this week, as well as we'll be solving some model questions, which is quite similar to your assignments and final exam. So this session is being recorded, so you can watch it later on YouTube. So let's begin. So we'll be doing the week 7, the part that was covered in week 7. So I will start with a brief recap what was done in week 7. So in the past 2 weeks, we have come across two concepts of solving the RL problem. One was Monte Carlo, another was TD0. Right. And previous to that also we have gone across dynamic programming concepts and all. So, but let's focus on these two for a second. So let me write the equation of a simple Monte Carlo. Okay. So in a simple Monte Carlo, each state update is given by V of st, V of st plus alpha gt minus v of st, right? So in a simple Monte Carlo, what we do, we randomly sample a trajectory or episode, sample a episode. We then follow the episode, we calculate the gain, and then we backpropagate the change in the gain to the first at every episode, right? So that's what we do. So, if you remember the algorithm of Monte Carlo, first Monte Carlo, that Monte Carlo algorithm, normal value update. So, if you remember that algorithm, what we are doing, we are just creating an episode. We are taking the generating an episode. We are from the last state. We start to calculate the return, and according to the return, we are updating the values. This equation serves that purpose, right? So instead of taking the average, basically for taking the average you have to store all the previous values iterated, right? So we can skip that. Like if you remember in the bandit solution, first we are doing an average, but after that we started to use a step function for that, right? So so this is, suppose you are in state, this is your state t, and after that it goes through many more states. Let's say this is your final t, right? So what does gt represents? Gt represents the return at state t, sorry, the return at state t, right? Gt represents the return at state t, and and you have your value st function, and after every iteration you update the value function as a incremental update, as an error propagation kind of step, right? So alpha here is your step function. Now if you remember now the Monte Carlo, so this one was your Monte Carlo. So let me now, okay, so let's first write the so what will be the value of gt? What will be the value of gt? Gt value will be r t plus 1 rt plus 1 plus gamma rt plus 2 plus gamma square r t plus 3 plus dot 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 plus r t, that will be gamma t minus 1, right? So this is your return at step t, right? So this is your Monte Carlo return, okay? So this also is called Monte Carlo return, okay? So now let's do the same for your TD0 to understand the difference, because that will be very helpful for you. Number 2 is TD0. Now what were we doing at TD0? What were we doing in TD0? We are just looking one step forward. Instead of computing everything, we are just looking the one step forward, instead of taking the whole backup from the terminal state to the state at which we are present, right? What we are doing here in TD0, we are just looking at one step forward. So if you are looking at one step forward, what should be your g? What should be your return at t at that case? Let's think about it. So let me draw it again. Okay, let's not use this frame. Okay. So let's write it here only. Number 2, TD0. So at TD0 we will consider only these two states, right? We are trying to, from this state we are trying to we are only looking at only one step, right? So what will be the gt in that case? Gt is equals to rt plus 1 plus gamma. What it will be? It will be gamma v t plus 1, right? Right. Essentially, so what does the value function represents? What does v represents? What does v represents? V is basically your value function, right? V is your value function. So what is value function? Is your expected return, right? So this is the return which you got, and you are doing a subtraction with the expected return to get the error in your expectation, and you are adding that error to your current value function, right? So in Monte Carlo you are doing it like that. Here also we will be doing the same thing, right? Instead of using this part, so if we consider this part, what it will be, what is this part basically? This part is basically gt plus 1, right? This part is basically gt plus 1, right? So we currently don't have the value of gt plus 1, but what we have currently is an estimation for that gt plus 1, that is your vt plus 1, where we will use that to compute gt, right? So that was what we are doing in td0, and the update function for your td0 was vs of t plus alpha plus alpha. What it will be? This g value rt plus 1 plus gamma v t plus 1 minus your this value v of st, right? So this is what your td0 was doing. So while td0 was only computing the gt by looking at the value of this, what was so this gt is called your gt of td, temporal difference, that is your td0, right? So while your Monte Carlo was looking way ahead, up till that, while Monte Carlo was looking way ahead up till this point, your your what is that? Your td0 was only looking one step ahead, right? That was your basic difference between your Monte Carlo and your td. Now we come to another point. Now our next target is, why are we just trying to do only one step or full step? We can target any number of steps, right? We can look ahead two steps at a time at the first step, two step ahead, or three step ahead, right? We can do that. Right, so we can do that. Now this in this week's class, what we come to something called TDN, which was looking in step ahead instead of just only one step ahead, right? So TD if we write TD0 as this, what will be TD1? What will be TD1? So if we write, so this is called G1. G1 one step look ahead is G1 at T, one step look ahead is RT plus 1 plus gamma V of t plus 1, right? That is your one look ahead step. Sorry, is t plus 1. That is your one step look ahead. Similarly, gt of 2, what it will be? rt plus 1 plus gamma rt plus 2 plus how much? It will be gamma square v of s of t plus 2, right? That is what your two step look ahead return is, right? Similarly, what will be gn? gt of n, what it will be? rt plus 1 plus gamma r t plus 2 plus dot 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 gamma n minus 1 v s of t plus n minus 1 plus gamma n v of s t plus n, right? Sorry, this one is wrong. This will be the r part. R t plus n minus 1, right? So this is your this is your n step look ahead return, right? Similarly, you can write an update rule n step look ahead as this, right? What will be the update rule for vst in this case? Same, vst is equals to v of s of t plus alpha g of t by n minus v of s of what it will be? S of t, right? It's the general update rule, except you are just replacing this each case. So if g1 it was for g0, the update was this. If gn for the update is this, for g0 it was this. So this was basically your same. So you can just rewrite this at this, right? v of st equals to v of st plus gamma g gt1 minus v of st, right? So you can rewrite it at the same way, right? So the essence of the problem is remains same. The update rule remains same. So you have your current value function. You have to update your current value function with the error we have received, whether it is one step look ahead, two step look ahead, or your n step look ahead, or if in case of Monte Carlo, it is all the step look ahead up to the terminal. So that's the main crux of your TD n, or your n step look ahead, whatever you want to say that. So any doubt regarding this?
No doubt, sir.
So so this part this part can be written as delta v of st, that is equals to alpha g to the power of n minus v of st, right? So this is your update rule. So this or update rule or backward error propagation, whatever you want to say, but this is the one which you will be adding every time to your value function. Okay. So that was the main crux of your TD0 in step ahead, look ahead, and your Monte Carlo. Now, now there is a question: when will you update the TD value? When to update the value function? So there are two ways you can do it. Generally, there are two ways you can do it. Either you can do it online or offline. Online means as you are visiting the state, you are updating the value function, and offline is after you have finished an episode, you update the value function, right? So those are the two steps you can do. Now there is another way. So another thing that has to be told. So this error propagation, or formally called backups, these are also known as backups, delta vt delta v is of t is equals to alpha gtn minus v of s of t. Like these are called these are called backups generally, or error propagation. Right. So you're currently at a state. So let's consider the example of TD0. So you're currently at state, suppose S of t, and this is your terminal. So in the forward version, or so what I was trying to say so far, these update rules and all, you are trying to update. You are trying to update by sitting here. So let's say you have gone through several steps in the between. So so you are at ST and you want to update the value which may occur in the future. From the future, you want to update the current value. So algorithmically, this is quite sound way of doing it, but that's not the only way you can do it, right? So you can do it another way. So either you propagate your value this side, or another way you can do it is you propagate your value this side. Suppose you have reached a state and you now want to propagate the value backward. You have reached an optimal state and now you want to update the previous value function based on it, right? These two ways can be do it. Either you can go look ahead and find out the optimal function according to your current mapping, or you can update your previous mapping by sitting at the position where you are. So practically thinking, which one do you think is more practical way of doing it? What is more practical way of doing it? Either going forward, looking forward, or you know what has happened before, you update the previous part. So this way of updating, this forward way of updating, so these are called forward way and backward way. So update forward, number 2 update backward. So these are the two ways you can do it. So, and while updation from forward, the complexity is much high because you have to go to the front and then do it. While backward update is much easy because you already know what has happened before. You don't have to follow the algo and everything. You just update whatever has happened before. You just update based on your current state. So that is quite mechanical way of doing it, and the update forward is called algorithmic way of doing it. Those are the two main steps to think about. Another concept which was introduced in this part, which is quite important and quite thoughtful to think about it actually, is your so suppose you are currently at state S, right? Then go to one step, or you go to two step, or you can do a three step look ahead, or you do a four step look ahead. So you understand what is the goal. So goal is to find an optimal policy, right? Now you can do a one step look ahead, you can do a two step look ahead, you can do a three step look ahead, or you can do a four step look ahead. Suppose you are trying to so the concept is you don't do only a one step look ahead or two step look ahead. What you do is actually a average. You take the average of the backups from each of these look aheads. So one option, let's say your GT average, let's say is GT average is, let's say you are taking into action both G2T and G24, and you do a half plus half proportion. So these are your probabilities, let's say, or not say probabilities, ratio. Right. So you have what I'm trying to say is, so you are at state S and you don't know which is one is the which one is your base rate and which one is your base policy. So what you can do is you can do a two-step lookup and you can do a four-step lookup. You get some value and you take it proportionately, right? Either you take half of G2 and G3 or some other fractions or ratios to calculate your GT average. Now from here, so this is your averaging out of your, this is your averaging of backups. So here comes the concept of TD lambda. TD lambda is an algorithm which is a particular way of calculating in step look ahead. So this algorithm is a particular way of calculating your in-step look ahead. So what basically does is an averaging of all the in-step look aheads. Okay. So that is what it does. I will write down the formula and try to explain as uh, as possible. So let me write down the formula. So the ratio. Okay, let me write the ratio for TD lambda. So the ratios are like this. So selecting this ratio is 1 minus lambda, 1 minus lambda lambda, 1 minus lambda lambda square, 1 minus lambda lambda cube, and so on. And for nth term it will be lambda t minus 1. This is for nth step. No, not for nth step, sorry. This is for your last step. That is your terminating step. For nth step it will be something like 1 minus lambda to the power of n minus 1. Now, since this is a ratio, if you add all these numbers up, it will come down to 0. So it will come down to 1, sorry. If you add all this up, it will come down to 1. So specifically, so since you are taking average, not an average, sum of ratio of a ratiotic sum, or sum of ratio of your n step look ahead returns. So this term is basically called GT lambda, which is given by 1 minus lambda summation n equals to 1 to infinity lambda to the power of minus n g t to t to the power of n, right? So this g to t to the power of n means so if gt to gt to the power 1 is one step look ahead, gt to the power of t plus 2 is 2 step, and gt to the power of t plus n is n step look ahead, right? So this is your return in case of your TD lambda algorithm. You are taking an average of all the, so this is your average, 1 minus lambda to the power of anything is your average. Now what will be the update? Update rule remains same, right? If you are doing a forward way of looking at it, as we have always discussed, it will be the same. V of s of t plus alpha gt lambda minus v of s of t, right? So update rule remains same. Okay, so now let's think about how to compute this part, how to compute it properly, because we are using the term infinity, whereas at state t it terminates, your episode ends. So GT lambda can be calculated as like this: 1 minus lambda. So let's divide it into two parts. N equals to 1 to t lambda to the power of n minus 1 g of t to the power of t plus n plus 1 minus lambda n is equals to t plus t. Sorry, this is not so this is not I made a mistake. T minus 1. T minus 1. T minus t. So this will be t minus t to infinity lambda to the power of n minus 1. Now what it will be? Suppose, so this happens after, so this loop, this part is the computation till your terminal state. So this is your computation till terminal state. So what it will be now? Will it be same after the terminal state? So after the terminal state, your you get that your reward, that is r to the power of n. So after that, it doesn't change. So you can write this as g of t. You have already reached your goal. So g of t, the maximum that you can get is here, g of t to the power of a. So that is the max you can get after you reach the terminal state, right? So this portion will remain same. Now we have to update this portion. So this will become, so this is basically a GT. So GT minus n, you can get it out because it is not required. So it will not be n, but since it is reached your final state, terminal state, therefore it is g to the power of mc, right? Monte Carlo, your Monte Carlo return. So you can, this is a constant, you can take it out. So it will become 1 minus lambda g to the power of t mc into n is equals to t minus t to infinity lambda n minus 1. T minus t. Now we can write this as 1 minus lambda g of mc into lambda t minus 1 lambda n equals to 0 to infinity lambda to the power of n, right? So this is a GP series, infinite GP series. So this sum will become 1 by 1 minus n. So this will become 1 minus lambda into g of Monte Carlo into t to the power t lambda to the power of t minus 1 into 1 minus lambda cancel, and this will be the term that will be remaining. So your g lambda can be written like this. So let me just delete some file. So your g lambda will something look like this. G lambda is equals to 1 minus lambda summation n equals to 1 t minus 1 lambda to the power of n minus 1 g of t is to t plus n plus lambda t minus 1 g of t of n. Right. Sorry, this will be g of Monte Carlo. Right. So that is how you can get your that is how you can get your g lambda value. So this one is your one part, and then this one is another part. Now let's consider. Now here comes the fun factor that will help you understand correlated between TD0 and Monte Carlo. So what will be the value if lambda equals to 0? So what will be the equation if lambda is equals to 0? So if lambda is equals to 0, this part will go to, so if lambda is equals to 0, this part will be 0, right? Lambda to the power something. So this part will be 0. What about this part? So that will be 1 minus 0 into this summation n equals to 1 t minus 1 lambda n minus 1 g of t, right? Now since lambda value is 0, so this term will also turns to 0 except one, except the value 0, except this value 0, 1 minus 1 g of t to t plus 1, right? So 0 to the power of 0 is 1. This will become 1 into 0 to the power of 0 into g of t is to t plus 1. So this will be 1. So it will ultimately g is equals to g of t plus 1. So what is this? What is this g? This is your g1, right? This is your g1. So this one is your g1 value, right? So uh, lambda 0, in lambda 0, g lambda is equals to g1, which basically means it will become a td0, right? So that means it will become a td0 when lambda value is 0, right? This is clear, right? How it is becoming 0. Okay, so now consider the case consider the case lambda equals to 1. What will happen if lambda equals to 1? This portion will become this portion will become 0. Lambda value is 1, 0, 0 into something is all 0, right? So g of lambda, so g of lambda will become 0 plus this one will not be 0 anymore. This one will have value because lambda is 1. So it will become g of t mc, right? So basically g of lambda is because to your Monte Carlo return, right? Right. So we look at to both the special cases. Lambda is equals to 1. So you look at both of the special cases. Lambda is equals to 1 and lambda is equals to 0. We looked at to both of cases and we saw that lambda is equals to 0 means you are doing a TT0 algorithm, and lambda is equals to 1 is basically a special case of your Monte Carlo algorithm, right? Now we will come to your backward view or your stresses eligibility test. Let me use a new Jamboard. So now let's look at eligibility traces. So so if you consider the case of forward update, so you are currently at state t and you are propagating the values from the front. So you are getting the value from the front and you are updating it. When you are at a backward update, you are currently at this state. You are currently at t is here. These are the states you have already traversed. Let's say this is your terminating state. What you will do is you will transmit your own update here. So this is called your back values. So you will correspond your back values from your state to the back. Right? So this is the main difference between your forward pass and backward pass. So for trace eligibility, we say now think about it. So this is a very interesting formula. Eligibility of stress is equals to lambda gamma e to the power t minus 1 s plus 1 lambda gamma e to the power t minus 1. So for this is for s equals to st, s not equals to st, right? So this is your eligibility trace for s equals to t and s equals to not equals to st. So what we are happening, so as you forward propagate, so what you are doing at each step, you are basically downgrading you're basically downgrading your updates. You are basically like uh, through a ratio, like your ratio is lambda and gamma. So you're basically downgrading your update. So let me just draw another graph, which I should have drawn before. Let me draw it now. Mm. So this is your ratio curve for your ratio curve for your forward propagation, forward update. Sorry. So for TD lambda, so this is your 1 minus lambda. So this is your fast. So this is your fast update, like state st and st plus 1. Then you come here. That will be your t plus 2 stage and dot dot dot. and this one will be your terminal state t, and after that everything is your that infinity part. Okay, so so you see the value constantly decreases, the proportion of the value constantly decreases. Okay, so this is your, that's why it is called, lambda is called your decay parameter. That means uh, your dependence. So when you are doing an n step look ahead, you are giving the highest priority or 1 minus lambda priority to your first to your first look ahead, and then you generally reduce, right? So this one will be your 1 minus lambda lambda, so this might be your 1 minus lambda lambda square and so on. So that is how you are forward propagating your back, right? So that is how your uh, lambda comes the decay parameter. Now let's come here. Now you have your lambda also here, decay parameter. And what is gamma? Gamma you have already understood previously from your from the days of your let's say MDP problems. You know what is gamma, right? Gamma is your discounting factor, right? So at each step what you are doing, you are just decreasing the eligibility of that state by this proportion, but only for the state which you are currently in you are increasing it eligibility, for other you are decreasing its eligibility by some proportion. So that is your basically your eligibility states. So in backward propagation you are always decreasing the eligibility of others by some parameter. So I will quickly write down the algorithm so as to have a better view of what we are trying to do and how it correlates with your parameters. So let me just pull it up. Okay, just give me 1 minute. I will just pull up the algorithm. It will be faster. Yeah. So this is your algorithm for backward update. So as I was saying, your decay parameter and everything. So this one is your eligibility trace. Okay. So you see, look at this. What we are trying to do is we are we have a we are for we have a pi and a state given from the episode, from initial episode. We take an action, we update this delta. What is this delta? So this delta you have already seen, it is one step look ahead, right? So you are basically calculating the update, right? R is basically return, is your reward. R is basically your reward. Now you are updating the E value for state S, for the state S, initial state S to be plus 1. For the state S to be plus 1. Now what you will do, you are doing this. What is this? This is basically your universal update. universal update. So what you are doing at the universal update, you are basically doing this, your step function alpha into delta, this difference. So this is quite common, and also you are multiplying it with the eligibility trace, right? What is the eligibility trace? So this is how. So you are currently, if I can draw a state, so you are currently at state this, you are updating. So who all are eligible for your update? You are eligible, this all are eligible for your update, not the this one. So their value will remain 0. Okay, so that is not an issue. Their value will remain 0. All you will be updating is this portion, and for updating that, for the portion you have already visited, and for updating that, you are sending your this error. So this is your backup. So you are sending your backup to this side. You are sending your backup here, and you are updating accordingly the value function based on your backup. You are basically doing a broadcast behind and doing your own backup, and then you are updating the eligibility of each of them, because you have already updated it once. So you are now those are less eligible for update from you again, right? So that is what it is trying to do, and then you update it. So this is your backward backward view of backward update of unity lambda of value function. So any doubt regarding this you can ask. I mean, this is a little complicated, but I'm sure. Okay, so this is your update rule for backward. Now let's consider uh, update backward. So now let's consider this one. Now let's consider the update for forward in case of action value pair. So this is your update for your action value pair. Okay. So previously you have done sarsa. This is your sarsa lambda. This is your sarsa lambda. So as previously, just like previously you have done sarsa, what you used to do, you have to take an action and take an action and observe its output, like what is the reward and next state. What you will do from the next state, you will choose an A based on the Q. So basically you are doing an alpha greedy update Now you are updating your similarly the delta function, same, I mean completely same, and then you are doing this the trace function update, and then you are propagating your trace backward, and then you are updating the trace again for each of them. This is updating your trace, updating all other trace. Okay, so this is what you have you this is your sarsa lambda. There is nothing much difference. So if you look at, so the only thing I will say in this one, which is quite interesting, is your e et s of a is basically gamma lambda e of sa plus 1 for s equals to s star, a is equal to at, right? Else it is lambda gamma lambda e of s of a, right? So nothing much difference. This is very quite common from your previous one. Okay, so any doubt regarding this? So one thing you will notice always, that once you have like, be it your uh, dynamic programming on your Monte Carlo or your TD0, so once you have derived the thing for your value function, for value function updates and all, you will see it completely just the motivation for your state value function is quite same, except in all of the cases you have to take an action from the next state, nothing more. Else it is all same, right? To generate that difference, to generate that backup, you just need to take an action, nothing difference, all same for the next state problem. In case of a q like state value action value function. Okay, so now next look at the last algorithm which we have was q lambda. Okay, yeah, so this is your q lambda. So for q lambda, what you should do for q function for your uh, q for your td0 q0, what you used to do for q0, you just used to take the argmax and calculate the rest, right? Instead of taking a specific action, you always used to take the max action. Here also you will do the same, but the update rule has little bit difference. So the update rule is little different. So et s of a is equals to, there are three options: 1 plus gamma lambda et minus 1 s of a 0 gamma lambda e of t minus 1 s of t. So this is the case when a is equals to st, a equals to a star equals to a equals to a star. Here it's the case is a is equals to st, a star, a dash is not equals to a star, and it is the a is not equals to st, right? Now there is a fundamentally there is a difference in q lambda. So what happens in q lambda is, so you can do a one step look ahead, you can do a two step look ahead, you can do a three step look ahead, or you can do a four step look ahead, or you can do an n step look ahead. But there is one simple catch. The catch is that this portion. So while previously we were reducing by a proportion, what we are trying to do is, if the current q, if current q is not optimal, we reduce the trace to 0. We are just simply reducing the trace for 0. We are saying that we will completely disregard it because it is not optimal. We will not look after it. We will not look up into the stress. So we are not going to explore that portion again. We are not going to explore those backtracking again. We will just explore the one which has a trace. So that is what this one is doing. So this, it is rejecting whatever, if there is any suboptimal q which we are trying to accumulate, because this a star, so remember this a dash, this a dash is sampled from q may be optimal, q not be something, but a star is your base to action at state s bar. So if there is a mismatch between a and a dash, that means the current what you have, current q which you have, it is not optimal, because a star is optimal whereas the current q are giving you a dash. So that is the one thing your this algorithm is different from your q0 algorithm. Okay, so any doubt regarding this you can ask. Okay, so that was the last part of this week's course, was that. So that was it. So let's now solve some of the problems for this week. Let's start solving some problems. Okay, so this is the first question. Consider example 7.1 and figure 7.2 in the textbook. Which of the following will result in decrease in RMS error shown in the graphs? So these are the two graphs you have. So this is online and this is offline. So what is online? Online means you are updating. So this is your T, current step. T and terminal step. So in online case, you will update Vt as you are progressing. As you are progressing, you will update the T. Whereas in offline mode, what will happen? You are currently here, T. The update will take place once you have reached here. Only once you have reached here from T to T, your T will be updated. Only when you have reached here. So that is the main difference. Okay. So the question is, which of the following steps will result in decrease in RMS errors in the graph? So these are your RMS errors. So these are your graphs. So this is your alpha value, this is your RMS error value, and so which of the following will result in a decrease in RMS error value? Also note these are the values of these all are these are all lambda values. These all are your lambda values. Increase the number of steps of MTP, increasing the number of episodes over which the error is calculated, increasing the number of repetition over which the error is calculated, none of the above. So also this RMS is over error over first 10 episode. Okay, the simple answer is what will result in decrease in the RMS errors? The simple answer is the number of episodes. If we increase the number of episodes over which the error is calculated. Why? Because as we explore more, the error will reduce. What do you mean by exploring? We are evaluating the value function, evaluating the policy mode. Sorry. Okay. So the correct answer is B, increasing the number of episodes over which it is calculated. So that will result in decrease in RMS errors. So if you, I don't want to say this, but this is not quite a phenomena of your TD lambda. So this thing will happen for any of your like MDP problems. Any of your Markov decision problem. So if you evaluate a policy more, you will have a better understanding of reducing the error. You have a better chance of reducing the error. That is quite common for all MDP problems solutions. Okay, so let's go to the next one. So consider an episodic task, and for lambda value 0 1, is it true that one step return always gets assigned the maximum weight in W return? So what do you have in W return? GW is equals to 1 minus lambda G G1 plus 1 minus lambda G2 plus 1 minus lambda square G3 plus 1 minus lambda cube G4 plus dot dot dot, right? So what the question says? The question says, is this the maximum weight that is given in the lambda return? Oh, so uh, go. Let's just say what will be the last value in the lambda return. Lambda. One is your 1 minus lambda t minus 1 g of t, that is your last step, and here is your others. 1 minus lambda to the power of t minus the n part. Okay. So is the statement correct that one step return always gets the maximum assigned random weight? Also note, since these are ratio, is adding all this up, adding this, 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 and this all up will be 1, right? So let us consider an example. Suppose you have an episode of length 3 and lambda is equals to 0.7. So then what will be the weights? What will be the weights? So your one weight will be 1 minus lambda, another weight will be 1 minus lambda, another weight will be lambda, because there are 3, right? So episode length is 3, so it will be 3 minus 1 minus 1. So it will be just lambda. Just lambda or lambda square, sorry. So its value will be, what will be its value? Okay, so t, right? So what will be the value of t? 3 minus t minus 1. So the episode length is 3, is 0, is 1, is 2, is 3. This I calculated, this I calculated, this I calculate. So it will be 0. P value will be 0. So it will become lambda square. Okay. So these are the three segments. So this value will come down to basically 1 minus lambda will be 1 minus 0.7 will be 0.3. This one will become 0.3 into 0.7, that is 0.21, and this one will become lambda square will become 0.7 into 0.7, that will be 0.49. So clearly this value is greater than this and this, right? So it is not necessary that w minus 1 will always have the highest value. It is not necessary. Okay, so the answer here will be no. Answer here will be no, because you can clearly see in this example that 1 minus lambda is less than lambda square. Okay, so let's go to the next one. So in the TD lambda algorithm, if lambda is equals to 1 and gamma is equals to 1, which of the following are true? Okay. So what is the TD lambda algorithm? TD lambda algorithm is the one where you are doing basically e to the power of s at time t is basically gamma lambda e to the power t minus 1 s plus 1 is equals to st, else gamma lambda e to the power t minus 1 is not equals to st, right? So that is how, that is your lambda does. So now it is saying that you have you they are saying lambda is equals to 1 and gamma is equals to 1. So which of the following will be true? So suppose if lambda is equals to 1, what will happen? If lambda is equals to 1, what will happen? So if lambda is equals to 1, will it be a TD0 or Monte Carlo? Which one it will be?
I think Monte Carlo.
Yeah, why? You don't have to substitute values. You can think logically and say. So because what is your lambda? Your lambda is a decay factor, right? So in Monte Carlo, do you decay your returns?
No, no.
No. So essentially it is a Monte Carlo, right? So basically you are saying that you are not discrediting any of the your path. You are just basically saying that it will have equal ratio. You are not saying that it will have one will have a greater proportion representation for the value from one state, from the terminating state and all. You are just simply saying that it is a you will have equal proportion for all of them. You will not have a variable proportion. So your proportional depends constant whether you are at the first step or at the last step. Okay, so that is clearly a Monte Carlo. Right, so this one is correct. So the eligibility traces do not decay. True, if lambda is equals to 1, your eligibility traces are not decaying. So this one is also true. Now the thing is, the value of all states are updated by TD error in each episode. Think about it. Is this true? Is it updated at each episode? Or it is updated at the end? So because it becomes a Monte Carlo, so since it is a Monte Carlo, what happens in Monte Carlo? You reach the end terminal and you then update, right? So this will also be the same. So it will not be updated by the TDR at each episode. It will be updated at the end of each episodes. So this one is not correct. Sorry, I said the opposite. Sorry. I said the opposite. Sorry, I said just the opposite. The value are not updated in each episode. It is updated as you go it, right? Your value updates as you go from here to here. Your value updates this thing, right? So that is a better fundamental of TD lambda, right? So TD lambda always back propagates your stuff, right? So it is not at the end of each episode, but rather every step propagation. So this one is not correct. So this method is not suitable for continuing task. So if you remember the MDV problem, what happens when gamma is equals to 1? What happens if gamma equals to 1? So gamma is your discounting factor, right? So if your gamma becomes 1, you are basically increasing your G value even if it is a continuous task, that is if it is not ending. So basically your G value will continuously gets increased. So this, if you remember the MDP original written formulation, it was mostly for your non-continuous task, right? So this method is not suitable actually for continuing task. So this one is correct. So to read more about this, you can go to MDP chapter and study the return. Okay, so let's go to the next one. Okay, so the question is, assume you have an MDP with S states. So you have an MDP with S states. Okay. So you decided to use a n-step truncated uh, return evaluation. Basically, you are trying to find G lambda. So do you think there is any utility in considering values of n which exceeds of this problem? So, so if you consider the G lambda formulation, right? So you have this infinity term. So basically, you are using it. Okay. So there is some utility to of using it, right? But why? So the simple answer is that you are using ratio sum, like a weighted sum, right? So let me use the better option, weighted sum. You are doing a weighted average. So if you follow this formula, if you just instead of following this formula, if you do it for the n equals to 1 to t minus 1 lambda minus 1 g of t is to t plus 1. So if you do it only for n steps, if you only do it for let's say t minus 1 step, that is one step less than your terminal state, so what will happen is that this will not be equal to 1. This summation will not be equal to 1. So you have to have this component like lambda to the power of t minus 1 g of t so that you can average it out, right? So you need that. There is some utility in doing that. You will get the absolute return, the Monte Carlo part. Otherwise, if you stop at one stop back, it will not be the correct one. You will not get the whole return. So correct answer is yes. Okay, so let's go to the next one. So which of the following are the reasons to support your answer in previous question? Okay, sorry, I missed a mistake. Sorry. I made a mistake. Sorry, I was thinking about the other part. Okay. So this question says that there are n states. So let's say A, B, C, D, E, F, G, H. Sorry, it was a wrong solution. So suppose you have 8 states. So is it saying that is there any utility of considering values of n, TD of n, greater than number of s? The answer is yes. So the answer is basically yes, because because your states can be something like this. Your episode can be something like this. It goes to A to B to C, then back to A, then D, F, then back to A, then B, then C, then H, not H, let's say G, let's say G, then B, and then it terminates at H. Suppose this is the terminating stop. So what is the episode length? So this is an episode length, right? This can be an episode. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 12. And what is modus? Modus in this case is 8. Right, clearly an example. This could be an episode. So the value of n can be more than s. That is quite frankly is possible. So the correct answer is B. Yes. So any doubt regarding this? Sorry, I thought about it a completely different way previously. Okay, so let's go to the next one. So this was the same question. Which of the following are the reasons to support your answer in the previous question? So the answer is what I said. The length of each episodes may exceed s. Hence, the value of n can be greater than s should be considered. Okay. It is the answer for that question. Okay, so let's go to the next one. So consider you have okay, I will give you the figure. So consider you have a fast visit Monte Carlo prediction algorithm and the TD lambda algorithm. If the two algorithm have will the two algorithm be identical if lambda value is 1? It's saying the lambda value is 1 for TD lambda. Will it be identical? this and this is your first visit MC, and this is your TD lambda. So there is one problem in this figure. Okay, so I made a mistake. So this is not first visit, this is every visit. Okay, so yeah, so uh, for every visit, is it basically same? So if it is every visit, for every visit, this is same. So for every visit, your TD lambda TD lambda for lambda is equals to 1 is your basically a Monte Carlo. And so what is the difference between first visit Monte Carlo and every visit Monte Carlo? Every visit is basically a online update, whereas first visit is a offline update. So basically, uh, if you are using an every visit and TD lambda equals to 1, it is basically same. But if you are using an first visit and TD lambda 1, those are different because one is doing an online update, another one is doing an offline update. Okay. Okay, so let's go to the next one. This is very interesting. So you are given a set of state. So this is your episode, right? So what is the eligibility value at this is 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, 8. So we have been told to find out the value of E7 S of 1, E7 S of 1. Sorry, I did the wrong counting. So this is the first step. 0, 1, 2, 3, 4, 5, 6, 7. So we have to find out the value of eligibility e to the power of S1 at value S1 at step 7. At this step we have to find out this value. Okay, so we can write this et of S state as something like this: summation k equals to 0 to t lambda gamma t minus k identity s of s. So we have to find out this given this. Okay, so at given state 0, e0 s1 is equals to 0. So this is accumulating stresses. So what happens in case of an accumulating stress is this. So suppose, so this is your update one, right? So this update one was et s of t is equals to, so in case of accumulating state stress, it will be something like this: gamma delta e to the power of t minus 1 is plus 1, or gamma delta e to the power t minus 1 is plus 1, not plus 1, just, right? This is a is equals to st, is not equals to st, right? What accumulating what your what this does, which one is this, replacing stress does, or replacing, this is your accumulating, what replacing stress does is ETS equals to 1 if A is equals to ST. It just changes its value to 1, else lambda gamma e to the power t minus 1 is not equals to ST, right? So these are two types of stresses. One is accumulating stress, another is replacing stress. So in your accumulating stress, you are for each step you are using the fractions gamma and delta to increase or decrease its eligibility. Yeah, so this one is increasing its eligibility by plus 1. Here what you do is you just set it to 1, nothing more. Okay, so this accumulating state it can also be represented by this formula: k equals to 0 to t, right? You have visited, so this is your, you are currently at state t, you have visited all the previous one, right, k states, and you want to accumulate, you want to find out what is the current value of uh, t at state s, right? So you will use this formula to update it. We have to find e7 s1, right? So what you will do is k equals to 0, k equals to 0 to t, that is t will be 7 delta gamma t value is 7 minus k is st, right? So st will be in this case, will be in this case 1. Okay, s equals to s1. Okay, fine. So let's do it. So this value I is equals to ISS1 will be 1 when you reach the state S1, else it will be 0. Okay, so first state there is no S1. Okay, the second state you have S1, so it will become 1. And what is the value of k in that case? 1. So it will be gamma lambda 6 minus 1, sorry, 7 minus 1 k value is 1 in that time, plus lambda gamma when we are next facing S1 at 4, 7 minus 4 plus lambda gamma when we are next facing at 6, 7 minus 6. Okay, so if we solve this, if we solve this, this will come out to be lambda 7 gamma 7 plus lambda 3 gamma 3 plus lambda gamma. Okay, so it will be option D. So any doubt regarding the steps, you can ask regarding this. Okay, so let's go to the next one. So you have this, so in case of accumulated trace, we will be using replacing trace. So let me again use it. S2, S1, S3, S2, S1, S3, S2, S1, S3, S2, S1, S2, S1, S6. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. Okay, what we have to find out? We have to find out E7, S1. Right. So in replacing traces, whenever you reach the state, what you will do? You will set it value to 1. So whenever it reaches here, it becomes 1. Whenever after that, what happens? So initially it was 0. Sorry, let me use another ink. So initially it was 0, then it becomes 1 when we reset it. Then what will become? Then we will again, it will get ratioed. That will become, uh, that will become lambda gamma. Then again it will be ratioed gamma square lambda square. Again it will be, again it is S1, so it will again become 1. Then again S2, so it will be again ratioed lambda gamma. Then become S1, it will again become 1. And then come S6, it will again be ratioed gamma lambda. Yes, so the correct answer is gamma lambda. So E7 will be equals to gamma lambda. Yes, so correct answer will be option B. Okay. So any doubt you have? So this was the last question. So if you have any doubt, you can ask. Yes, thank you for joining today. We will again meet next week. Yeah, thanks for joining. Yeah,
Thank you, sir.
yeah, thank you for joining.